YouTube? It's your boy JOSHABRAHAM. We're having the sequence analysis class in about 1 hour, so I gotta make sure I do a presentation. I gotta make sure I am able to do the presentation if asked me to. What am I even doing? Yes. So, where is my answer that I uploaded? This is my answer. Transition probability, initial state probability, two hidden states, P initial equals 2, normal, therefore, according to the I'm gonna close the window. Oh, it's cold. The pencil should be pretty charged right now. Yep, 83. That's pretty good. Let me just make sure if I have the class, Because something in me is telling me that there might be no class, but it's most likely, yeah. Yep, there is the class. I'm part of 265, right? Because okay, so okay, okay. Before the class, we got. Mm-hmm. So can you explain to me how do I start the explanation? Like I don't exactly know what the transition matrix here is, or the initial state probabilities, etc. etc. Like a lot of terms that I don't know right now. Start explaining to me so that I can do this. These distributions are necessary to calculate PEXTUT. Okay, okay. All right, let's structure this so you can explain clearly in your presentation. We are analyzing DNA copy number variation using hidden Markov model The goal is to infer how many copies of DNA segment are present based on the probe intensities measured on DNA microarray. Each probe corresponds to a DNA segment, and higher intensity means more copies are likely present. Higher intensity, each pro. Okay. The goal is to infer how many copies of DNA segment are present based on the probe intensities. Explain the observations. The observation are measured intensities of for 5 consecutive DNA segments. Now, what was consecutive DNA segments? Each intensity is a real number representing how strongly DNA from a sample bound to that probe. This is what the data we see in HMM. Hidden states. There are 3 hidden states: deletion, normal, amplification. We don't directly know which each segment is in. That's where they are hidden states. Initial state probabilities. These probabilities tell us the chance of starting in each state for the first probe. 2% chance first segment is deleted, 95% chance it's normal, and 3% chance it's amplified. These probabilities tell us the chance of starting in each state for the first probe. This is our prior knowledge based on biology. Most segments are normal. Transition matrix. This matrix tells us the probability of moving from one state to another between consecutive probes. Example. Row equals current state. Column equals next state. Like A, 2, and 3. Yeah. 60% chance of going from normal to amplified in the next segment. It encodes dependency between consecutive DNA. Okay, I did not get that. I need to learn more on that one. Hey, series out of time for 10 minutes. Emission probabilities. Each state has a mean and standard deviation from probe intensities. Formula, this gives the probability of seeing the measured intensity if the segment is in that state. So transition probability, initial state probability. 3 hidden states. We have 2 hidden states, or 2 sets of hidden states. Given the sequence of hidden states, these 5 hidden states correspond to an unknown copy number in each. Which of those is more likely to be observed? So the initial probe intensity given for both of these sequence of hidden states is 2. That means the probe intensity shows a normal normal what? Chance it's normal. What do you mean? Well, normal what? Probability of hidden state sequence, there's an equation where probability equals the initial state, the value of initial state multiplied with the product of transition state number 2 to how many hidden states are in this sequence. Like for our question it would be 5. Time index / position in the sequence of hidden states. XLP of I it's what do we understand from this? Hmm, hmm, hmm. What is a probe? A probe is a short known DNA sequence that is attached to a microarray chip. Each probe corresponds to a specific region of the genome. A probe is a short known DNA sequence that is attached to a microarray chip. I'm still. What is this thing, bro? What is this microarray chip? Microarray chip is a lab tool with thousands of known DNA sequences fixed to a solid surface like glass used to simultaneously measure the activity of the genes in a sample by seeing which probe binds to fluorescency labeled as DNA, RNA from the sample. Each probe corresponds to a specific region segment of the genome. Probe 1 might target the first 1,000 base pairs, of probe 2 might be the next. Okay, okay. What happened during hybridization? You take the DNA from your sample and label it with fluorescent dye. You wash the sample. Okay, okay. What is probe intensity? After washing away the unbound, you take the DNA from your sample Label it with the fluorescent dye. You wash the sample over the chip. DNA from the sample will stick to the probes that are complementary. The more DNA there is for that segment in in your sample, the more molecules will stick to the probe. The more DNA there is in that segment in your sample is for that. The more DNA there is for that segment in your sample, the more molecules will stick to the probe. What is probe intensity? After washing away unbound DNA, the chip is scanned with a laser. The spots emit light based on how much DNA is bound. The emitted light is measured as the numerical intensity. Higher intensity, more DNA bound, higher copy number. Low intensity, less. Uh, DNA segment is lightly amplified, more than 2 copies. How does this copy work? Medium, DNA segment is normal. Wait. So here, the medium normal means the sample DNA that we introduced has joined as complementary in one of the section in the probe, and that's it. But high intensity, does that mean after joining as part of complementary, did that new sequence of sample and the one in the probe starts to replicate itself, and the low intensity, does that mean less of the sample is joined as part of complementary to the probe? Not quite. The intensity doesn't mean replication is happening. The probe has DNA attached to a region that matches the sample. Normal amount of DNA binds to the form. That medium intensity reflects the expected number of DNA copies in a diploid genome. Nothing replicates here, it's just binding, not replication. More DNA from the sample binds to the probe than expected. This usually means the sample has extra copies. This usually means the sample has extra copies of DNA segment, not that it replicated on the chip. The probe itself does not replicate, it just detects more DNA from the sample. More sample. The sample has extra copies of that DNA segment. High intensity is just a signal that more DNA is present in the sample. More DNA of what? More DNA of similar. More DNA Of what? Like of complementary to the probe? How DNA microarrays are built. Oh, can I see the image bigger? Okay, I understood that the 1, 2, 3 of probe intensities can you continue that with the next part? Like, I didn't get the transition matrix. Perfect. Now that you understand what the intensity means, let's move to the transition matrix part in HMM. Not H&M. Wait, HMM, that's the store, right? That is the name of the store. That is basically it. Dude, I got 10 minutes before the class. I'm not making it, bro. I'm not making it. Yes, you are. Yes, I am.
I feel lost.
He's seen a significant unknown copy number as an unknown copy number. These are hidden states because you don't directly observe them, you only see the intensities. Transition matrix. This describes the proper probability of moving from one hidden state to another for consecutive DNA segments. Okay. Now for this, going from one hidden state to another, one hidden state to another, one hidden state to another. I'm still confused on the one hidden state to another. I'm still on the micro array chip, and are we using different samples with the same probe, or what? What do we mean by unknown like are we okay? I'm still I mean, a lot of loopholes. What the hidden states are. When you do the microarray, you measure the intensity of each probe. That's your observed data, but the true copy number of DNA segment that the probe is targeting is unknown. That's what HMM calls the hidden state UT. We don't directly see the copy number in the wet lab. We only see the light intensity. That's why it's hidden. What? Say what? That's observed data, but the true copy number of the DNA segment that probe is targeting is unknown. True copy number. We don't see the copy number in the wet lab. We only see the light intensity. That's why it's hidden. But the light intensity should let us know if it's we don't see directly the oh. Wait, you just explained. Let me first read this. What moving from one hidden state to another means. DNA segments are consecutive along the genome. Copy numbers of neighboring segments are not independent. The transition matrix codes how likely it is for a next segment to have same or different copy number from the previous segment. Examples: transition row for normal state. Thus the row sums are 1. And the previous segment was normal too. If the previous segment was normal, the next segment. Okay, there's only 1% chance that the next person is deletion. The next segment is deletion. There's a 39% chance. Okay, interpretation copy numbers can change along the genome, but some changes are more likely than others. Okay. Are we using different samples? No, HMM looks at one DNA sample at a time. All the probes of the microarray come as the same DNA samples targeting different segments of the DNA. Okay. Different segments of the DNA. Some parts complement now I'm now my next doubt would be what is in the probe. Now my another doubt would be what's in the probe that makes these sample to attach complementarily. Like The probe in the microarray should have complementary complementary strands of the sample to have the normal or amp detection. Doubt. Light intensities gives a clue, but it's not perfect. That's why the copy number is still hidden. Again, copy number. What do you mean by copy number? Means amplification, but there's noise. Maybe the probe didn't bind perfectly, or measurement has error. Similarly, high intensity usually indicates 2 copies. Emission probability. How likely its observed intensity gives a particular state. How likely is the hidden state to change from the previous segment? Okay. Think of the probe of microarray single strand DNA sequence that is designed to be complementary to the. I think from the probe we. Okay, so is this how we sequence? So basically, is this how. So is this basically how we sequence the genome of an unknown organism, etc.? Not exactly, but it's related. Okay. Okay, I'm a bit confused on the term copy number. Copy number simply means how many copies of the particular DNA segment are present in the genome. How many copies of the particular DNA segment are present in the genome? Copy number simply means how many copies of particular DNA segment are. So the hidden states of HMM is just a numeric label for the copy number. The HMM's job is to guess the most likely hidden state for each DNA segment based on the observed intensity. HMM's job is to guess. Okay, I'm still a bit confused on the amplification part. Like let's say a probe has a specific complementary strand, and the introduced sample both, let's say, are have segments 1000 BP. How does the higher intensity one work? Like, after the complementary strand joins with the appropriate segment of the sample, how can there be more attaching there? There won't. My mind is telling me there is no space for more segments of the sample to attach to the probe. And that's already reached the normal intensity that we are talking about. I'm a bit confused on the gain slash amplification. I don't know why, maybe I'm stupid, but I cannot physically imagine what do you mean by amplification. The key is microarray doesn't measure literally how many molecules fit on the probe. It measures the total DNA bound to the probe. Probe is fixed on the chip. It's a short DNA sequence. It's complementary to specific segment of the genome. You add your DNA sample, it usually fragmented, so there's a lot of copies. Hybridization happens. Each DNA fragment that matches to the probe can stick to multiple copies of the segment from this multiple copies of the segment. If the segment is present normally, deployed. If the segment is amplified, higher. If the segment is deleted, fewer fragments bind, lower intensity. Important. The probe itself doesn't expand or make space. It's not about physical space. The chip measures the total fluorescence from all DNA molecules that bound. So higher copy number in the genome, more DNA molecules in the solution. Higher copy number in the genome. Think of each probe as a parking spot. Normally, 2 cars arrive, medium signal. If a parking lot, again, I'm guessing this probe the sample, but um uh, fused. I forgot a bit on the deployed part, but okay, I kind of get it. But uh, how is a lot of just random segments of DNA of the sample is gonna attach to the probe. Okay, try explaining with what makes this amplification happen. What part of the, what makes the probe have more sequence segments of DNA to DNA of the sample to attach than the normal deployed. And what makes it to have deletion slash less segments attached to the probe? What factor in the probe changes these? The probe itself is fixed. Each probe in the microarray is a short DNA sequence that is complementary to a specific region of the DNA. The probe does not change. Its sequence, length, position is fixed. Nothing about the probe itself causes amplification or deletion signals. What varies in the DNA sample? The DNA sample is fragments. The DNA sample is fragmented into many pieces, so there are a lot of copies of each genomic segments in the solution. In solution, copy number refers to how many copies of the segment exist in the genome itself. How many copies of the segment? How many? The same copies. Okay, okay. Usually two copies of the DNA segments. Okay, okay, okay. Uh-huh. Deletion. So, okay. So, amplification genes sequences could say that sequence could represent the gene for something that's not just specific to that organism. If I'm wrong, I'm still okay with more control. I'm guessing ChatGPT is gonna say it could mean that, but it's not gonna always exactly okay. Amplification just tells you that the particular genome you're measuring, that there are extra copies of the DNA segment. It doesn't mean that the sequence is foreign or from another organism. It's still part of the organism genome. Sometimes, due to natural variation, some segments are duplicated. These extra copies can influence traits, genomes, expressions, disease susceptibility. The sequence itself is same as DNA's organism's DNA, just present in more copies. Conversely, deletions mean organism has fewer copies, but again, it's still the organism's own DNA. Okay. Okay. Now I kinda start starting to understand the transition matrix, but let's say in the sample the second row, which should be representing the normal copy, is specifically I'm still on the first question. God damn it. Got him. The transition matrix tells you probability of moving from one hidden state in one segment to another hidden state in the next consecutive segment. Rows are current state, columns are next state. If the current state segment has a normal copy number, there's 5% chance the next segment will be deletion. Ah. There's 90% chance. Okay. Okay. Now I need you to explain the probability of hidden state sequence. What is hidden state sequence? Okay, now I need a quick explanation on the hidden state sequence of 5 given for the question from the given from the question, like, are those numbers of hidden states measured or thought to be measured of different or 5 probes of the same microarray chip? Let me wash my mouth and face. It is fucking tiring, brother. Night the light lit. The data. Okay. Now in the equation for the probability of hidden state sequence, it starts with the P initial. Could you explain that one? Like why, and is that number like common? Common? Yes, the initial state probability is the probability of that the first unit segment is the particular hidden state before any transition state. A sequence is dependent. HMM models a sequence of dependent states. To compute the probability of full hidden state sequence, you must start with the probability of the first state sequence, then multiply by the transition probabilities for each subsequent states. Sure, let's go step by step. It's coming up. It's slow, but it's coming up. If I use my keyboard, no, if I use my like the cable, maybe it makes a difference. I don't know. I'm not sure. Allow. That's too slow, bro. I got 10 minutes. 'Observed light intensity from the microarray are continuous measurement naturally vary around the expected value. Here's hidden states represent copy numbers, deletion, normal, amplification. Oh, it's not showing up. one having a transition from normal to amplification, and from amplification to again back to normal, while the V is just straight up normal. P initial here both have 2, so it's normal. It's just 0.95% chance. It's 0.95 is just like 95% probability, which is usually the case. So the formula is PU equals P initial. I don't know, I forgot the name of the symbol, but it's like multiplying these probability numbers from the transition matrix. Could you see that there's 2% chance for deletion. Okay, YouTube, I'm gonna end the stream because I gotta go for a presentation. I hope it turns out well. Well, I gotta say there was a mistake. The deletion goes to the this part, and the amplification is here. Well, peace out YouTube, peace out Twitch.